So the ride, yeah. I'm not going again. I did it once for science, so I hope you appreciate it. So the ride, it starts over here. And it has what we physicists like to call a energy it has due to motion. So you just sit down in this thing. It doesn't crank you up or start you in gently. It just fires you straight out at about 90 miles an hour. Okay? You put the harness in and bang, you go. So you have a lot of kinetic energy when you start at the bottom of this roller coaster. And it doesn't mess about. It's just straight up, and you go straight up. I don't know how high that is. It's like 200 meters high. It's ridiculously high. When you reach the top of the roller coaster, most of that kinetic energy gets turned into potential energy. So you've gone up there, and you have potential energy. I just mention at this point, sometimes it doesn't reach all the way to the top. It gets nearly to the top, and it just rolls back to where it starts. When it gets to the top, of course, it rolls back down, hopefully forwards, not backwards, and it turns back into kinetic energy. So this happens to any time we have anything moving in and out of a gravitational field. If you're going up away from gravity, you lose that energy. And if you're coming down, then you're going to gain that energy. So that happens with a roller coaster. What about light? So I've got a little laser in here. Turns out light is actually affected in kind of a similar way. Let's take a look at what happens. So we've got a star over here. Star is a really good thing to consider because, first of all, it gives out a lot of photons. So it has a very strong gravitational field. And as the photons are escaping this star, they're climbing out of the gravitational field of the star. But photons can only travel at the speed of light. They're not allowed to slow down, but they do still lose energy as they're escaping this star. And the way photons do that is by getting stretched to longer wavelengths. So light has wavelengths, and shorter wavelengths are kind of blue colors, longer wavelengths are red colors. So the photon is a little cartoon, kind of does something like this. So if it started with, say, a blue wavelength, which as that photon climbs out of the star, it actually gets stretched to longer and longer wavelengths, and eventually it gets to kind of red wavelengths. It's a very, very subtle effect on Earth, but we can detect it. It doesn't happen nearly as much as this in a star. This is just kind of to illustrate what happens, but this is kind of what goes on. What about in a galaxy? So we've got these incredibly distant galaxies. Let's imagine, so this is kind of representing the Milky Way, and this is another galaxy over here. What happens to a photon as it's traveling towards us from a distant galaxy? If there's no change in the distance between these two galaxies, there's not going to be any net change in the wavelength of that light. It's going to end up being the same color as it started. It might lose some energy as it comes out of the galaxy, but just like a roller coaster there's going to be no change in the wavelength or the color of that light. What about if the distance between those two galaxies decreased as the light was traveling towards us? So in this kind of situation, the galaxy starts up here, and then it ends up closer. This is a very similar situation to that roller coaster rolling down a hill. So the photon is actually going to pick up energy as it's traveling towards us. So if it started out with this, pick up more energy, and it's going to end up as this kind of color. And we call this a blue shift because the color of the light gets shifted towards bluer colors. And what about if the distance increases? Well, it's the opposite effect, and we call this a redshift. So the distance is increased as that photon is traveling towards us. The photon loses energy, and it gets shifted towards redder colors, and we call this a redshift. Idea of what's going on. How do we actually measure this with our telescopes? So you probably saw some images of telescopes just before the talk. Quite often telescopes, they just take a picture of the sky, very much like what your camera does. So it takes a picture, you get a rough idea of what the color is. If we want to detect this shift in the light, we need to be a bit more accurate with how we measure the color of that light. So what we actually do in a telescope, you might have seen some glasses like this. They're called diffraction glasses, and they split light up into all of the different colors. And when you put it on, it looks really cool. And any light source gets split into lots of different colors. And we essentially put some glasses like this over our telescope. I mean, it's a little more technical, but fundamentally it's what we're doing. And it splits the light up into all different colors. Now, I'm sure you're all wondering, where can I get such a stylish pair of glasses like this myself? But don't worry, because I bought enough for everybody. Everybody gets a pair.